Hi, good morning EOCQ students. Today we are going to continue our physics lesson, and you can open your textbook page 502 for the EOCQ. For today's assignment, you need to do number 1, 2, and 3. And this is how to do number 1. An antiproton is identical to a proton except that it has negative charge. If a proton and an antiproton collide, they are annihilated and two photons are formed. Annihilated means disappear. Okay, so this proton and antiproton, when they collide, they will disappear and then two photons will be formed. For number 1a, calculate the energy released in the reaction. For this one, still simple. By using E equal to mc squared, then we can find the energy released in this reaction. Remember that here, there are one proton and one antiproton which has the same mass. So, 2 times the mass of proton, because there is proton and antiproton, times c squared. Find the answer. For number 1b, calculate the energy release if 1 mole of protons and 1 mole of antiprotons were annihilated by this process. So, by knowing the Avogadro constant, 1 mole is equal to 6.02 times 10 to the power of 23. So, the energy release in this reaction just simply times the energy times the Avogadro constant. Then you will get the total energy released by 1 mole of protons and 1 mole of antiprotons. Or, if you want to calculate it one by one, also possible. 1 mole of protons consists of this number of protons, and 1 mole of antiprotons also the same. But when you times with the energy, you need to divide by 2. This energy you need to divide by 2. Why? Because this we directly times it for antiprotons and protons. But here, if you want to calculate it one by one, then you will get actually the same answer. Next, for number 2, calculate the mass that would be annihilated to release 1 joule of energy. For this one, it's very simple. We just need to use E equal to mc squared, then rearrange to find the mass. Mass equal to E over c squared. The energy is 1 joule. Find it. And for number 3, in a nuclear reactor, the mass of uranium and the fission fragment falls at a rate of 70 milligram per second. It means that every 1 second, there are 70 microgram, sorry, not milligram, but microgram, 70 micrograms of uranium will reacted. And we can still use this formula to find the power output from the reactor, assuming that it is 100% efficient. So the mass, as I've mentioned just now, it is 70 microgram. So we just need to change the micro. 70 times 10 to the power of -6 times c squared, then you will find the energy. After you find the energy, then you need to put to the formula of power. Power is energy over time. The energy from here over the time. The time is per second, so we just need to put 1 second here, and then you will get the power in watt. Okay, guys, I think that's all for today. I hope you can do it by yourself, because today's question is still very simple. And submit to me today before 4 p.m. Thank you and bye-bye.